I want you to start by visualizing a really complex machine.
Oh, like a robotic arm.
Yeah, exactly. A robotic arm on an assembly line. Or it could be a massive HVAC system for a skyscraper. Or even, a conveyor belt at a huge shipping facility. Now, if you strip away the sheet metal, if you take off the casing, you can think of that machine almost exactly like a human body.
Right. You got the physical structure.
You have the steel frame, which acts as the skeleton. You have the motors and the pistons, which are basically the muscles doing all the heavy lifting. But the real question is, what tells those muscles to contract? What regulates the heartbeat of that machine?
Well, that would be the nervous system. Because without it, the muscles are literally just dead weight.
Exactly, the nervous system. And in the world of industrial engineering, that nervous system is the control circuit. It's this invisible web of logic that dictates every single movement, every pause, every safety stop. And today, we aren't just talking about how to build that system, we are talking about how to map it. We are diving deep into the architecture of AutoCAD Electrical.
Which is, I think we need to say right up front, a completely distinct beast from standard AutoCAD.
Oh, absolutely.
A lot of people, and I see this all the time, they assume it's just the same old drafting software, but maybe with a few extra buttons on the ribbon. But the underlying logic is fundamentally different.
And that is actually the core theme of the source material we're looking at today. We've got a really detailed technical breakdown from Suntech Engineering Solutions, and it really dissects this transition from simply drawing lines on a screen to actually engineering intelligent systems.
It's a huge paradigm shift.
It really is. And that's our mission for this deep dive. We want to take you from thinking about pixels on a screen to thinking about data in a database. We're going to completely unpack the mechanics of ladders, the physics of wires, the logic of components.
And the disasters.
Oh yeah, the absolute disasters that happen when you ignore the fundamental rules of the software. Because you can really mess things up.
You really can. It really is all about a shift in mindset. Because, when you draw a line in standard AutoCAD, you're basically just creating geometry.
Right, it's just a shape.
Exactly. It has a length, an angle, a position on the screen. But when you draw a wire in AutoCAD Electrical, you are creating a database entry. It just happens to have a visual representation so we humans can understand it. But underneath, it has electrical properties, connectivity. It follows the laws of physics.
So let's start where every single electrical designer starts. The blank page.
The dreaded blank page.
Right. Now, in the standard drafting world, you might just start, sketching a box or drawing a random line. But in this environment, you have to build the structure first. You have to build the ladder.
The ladder diagram.
Yeah.
It's foundational. It really is.
Yeah.
It is the industry standard for control circuits, particularly in North America. And it's called a ladder for a very literal reason. It looks exactly like one.
Which is always nice when technical terms actually make visual sense.
It's rare, but we'll take it.
Yeah, right.
So you have two long vertical rails running down the sides of the page, and then you have a series of horizontal rungs connecting them.
But, reading through the Suntech breakdown, I had to ask myself, why this shape? Is it just tradition because engineers have been doing it this way since the 1940s? Or is there a functional engineering reason why we organize this incredibly complex logic into a simple ladder format?
It's purely functional. It's actually brilliant. It perfectly visualizes the flow of power in a parallel circuit. So think about those vertical rails, the sides of the ladder. In the software and in physical reality, inside the control panel, those are your bus wires.
Okay, so they represent your main power supply.
Right.
So if we were dealing with a DC circuit, one rail is your positive bus and the other rail is your negative bus.
Yep. And if it's AC, it's your hot and your neutral.
So you have this potential energy, this voltage, just standing ready at those vertical rails.
Precisely. The energy is waiting. And then the horizontal lines, the rungs, those are the paths where that energy bridges across from hot to neutral or positive to negative.
And that is where you place your workhorses.
Exactly. That's where you put your relay coils, your pilot lights, your solenoid valves. Because they are arranged like steps on a ladder, every single rung receives the full voltage from the bus rails. It's a clean, perfectly parallel distribution of power.
So it's not just a drawing, it is a literal schematic representation of physics. It shows how the electrons are actually going to flow.
Exactly.
Now, bringing this into the digital space, the source material walks us through the insertion methods, how to actually get this ladder onto your screen. You can obviously hunt and peck through the ribbon menu under the wires tab to find insert ladder, but the breakdown explicitly suggests that power users, the real pros, usually bypass mouse entirely.
Oh, absolutely. AE ladder. That's the command.
KE ladder.
Just type that directly into the command line. You completely bypass all the menu digging and go straight to the configuration dialog box. And this is where the smart part of AutoCAD Electrical kicks in immediately. Because right away, you aren't just drawing lines, you are setting up the rules of the game for the entire drawing.
Yeah, I was looking at the screenshot of that dialog box in the source, and it is dense. There are so many parameters. You've got width, spacing, length.
And those are the physical geometry settings. Width is obviously the physical distance on the page between your two bus rails. Spacing is the vertical distance between each rung.
But the setting that really caught my eye in the research, and the one Suntech highlighted, was reference numbers. The source mentions you have a choice, basically, between numbers only and numbers and ruling.
Yes, and this is critical for the entire life cycle of the machine you're designing. Because you have to remember, you aren't just designing this schematic for yourself.
Right, you're designing it for the person who comes after you.
Exactly. You're designing it for the maintenance technician who has to troubleshoot a broken machine 5 years from now at 3 in the morning. They need a map. They need a coordinate system.
So the reference numbers give them that map.
Right. Reference numbers usually run down the far left side of the ladder. So you have line 1, line 2, line 3, all the way down. It gives you a clear y-axis index.
And what about the numbers and ruling option?
That option actually draws a physical grid, almost like light graph paper, right across the drawing area. It could be helpful for really dense drawings, but honestly, most designers stick to numbers only. It keeps the drawing much cleaner. But the underlying logic is exactly the same. You need to know exactly where you are on the page at any given moment.
And there's also the start index setting. That lets you customize where those numbers begin, right? The software obviously defaults to starting at the number 1, but you can override that.
You can, and you often absolutely should.
Why?
Well, think about a massive project. Say you have 50 pages of schematics for a huge assembly line. You can't have line 1 on every single page.
Oh, I see. You'd have 50 different line 1s.
Complete chaos. If a technician says, hey, check the relay on line 1, you wouldn't know which page they were talking about. So standard practice is to tie the line number to the page number. On page 10, you might set the start index to 1001.
Okay, so page 10, rung 01.
Exactly. And on page 20, it's 2001. The brilliant part is that the software takes that single seed number you enter and auto increments for every single rung below it. 1001, 1002, 1003, automatically.
That auto-incrementing feature is a subtle but incredibly powerful example of the database doing the heavy lifting for you. You aren't sitting there manually typing text boxes.
No, that would take forever.
You set the rule, and the software executes the math.
It completely eliminates human error in numbering. But there's another setting in that dialog box that I find really fascinating because, to a beginner, it seems totally counterintuitive.
Which one?
The visual styles. Specifically, there's an option to draw a ladder with no rungs.
Yeah, that actually stopped me for a second when I was reading the breakdown. Why on earth would you want a ladder with no steps? It's just 2 vertical lines and a column of numbers floating in space.
It seems weird, right? But think of it as a skeleton or a placeholder.
Okay.
In the very early stages of design, you might know for a fact that you have a 120-volt power bus running down this specific page, and you know you have exactly 30 lines of available vertical space.
Because of the page size.
Right. But you haven't engineered the specific control logic yet. You don't know where the relays and switches are going to go. Or, and this is very common, perhaps you know you're going to insert a massive component later on, like a variable frequency drive or a large PLC module that simply doesn't conform to the standard half-inch rung spacing.
So you place the no rungs ladder to reserve the physical real estate on the page and to reserve the logical address space in the database, but you leave the actual drawing area completely clear for custom work.
Correct. It defines the boundaries of the playing field without forcing you to spend 10 minutes deleting a bunch of pre-drawn lines later. It's a huge time saver if you plan ahead.
Speaking of reserving space and planning ahead, we definitely have to talk about the skip feature. Because the Suntech material highlights this as a tool that solves a very specific, very annoying headache.
Oh, the headache of the ghost rung.
Let's lay out the scenario for you. Let's say you are building a standard ladder. It's got typical 0.5-inch spacing. You're cruising along, you get down to rung 15, and you suddenly realize you need to put in a field device that is physically quite large, maybe a massive transformer that takes up 3 full inches of vertical space on the drawing.
Right. Now, if you just keep the standard ladder with all the rungs drawn in, you are going to have horizontal wires running right through the graphic of your transformer.
Which just looks terrible.
It looks sloppy, it's confusing to read, and technically it implies an electrical connection that doesn't exist.
Exactly. So how do you fix it without messing up the whole page? You use the skip setting. You tell the software, I want a ladder with 20 total rungs, but I want you to skip rungs 15, 16, and 17.
And so physically, on the screen, there is a visible gap. The vertical rails keep going, but there are no horizontal wires in that section.
Physically, it's empty space ready for your transformer, but logically, and this is the absolute key to understanding the software, the database still holds those numbers.
Yes.
The numbering sequence down the left side goes 14, then there's a huge physical gap, then the next rung down is 18. The numbers 15, 16, and 17 are skipped in the drawing, but they are fully accounted for in the background index.
And people always ask, why is that important? Why not just have the sequence go 14, then put the gap, and start the next rung at 15?
Yeah, why have missing numbers?
Because eventually, you might need to reference that empty space. Or, more likely, if you change the design later and insert a small component into that space, you don't want to have to renumber the entire remaining 50 pages of the project just because you added a gap on page 1. By skipping logically, you preserve the structural integrity of the numbering system across the whole database. You isolate the change.
It keeps the map totally accurate, even if the territory itself has a giant hole in it.
That's a great way to put it.
Now, despite all this careful planning with skipping and start indexes, we all know the reality of engineering. The first draft is never, ever the final draft. The oops factor is very real.
It is entirely inevitable. Design is an iterative process. You're going to make mistakes or get new requirements.
So the source material spends a really good chunk of time going over modifying the circuit skeleton. Let's say I built my beautiful ladder, I numbered it perfectly from 1 through 20. I step back, look at the print, and then I realize I completely missed a circuit. I need to add a brand new rung right between line 10 and line 11.
Okay, so the absolute novice move here, the thing you do your first week using the software, is you select the bottom half of the ladder, hit delete, and redraw it from scratch.
Please don't do that.
Do not do that. It ruins the database links. AutoCAD Electrical gives you a specific tool for this called Add Rung.
And how does it work?
It's brilliantly simple. You just activate the tool and click in the empty space between rung 10 and 11. The software automatically inserts a horizontal wire. It creates a new reference number for it, and this is where the magic happens. It automatically ripples the renumbering down the entire rest of the ladder. So the old 11 becomes 12, the old 12 becomes 13, and so on, instantly.
But the expert knights in the SunTech breakdown pointed out a hard constraint here. The database is smart, but physics still applies to the drawing.
Yes, very much so. The software is incredibly smart, but it's not going to allow you to break the laws of geometry.
What do you mean?
Well, you can only use the add rung command if there is actual physical blank space on the page to do so. If you initially set your rung spacing to 0.5 inches and you try to jam a brand new rung into a gap that is only 0.2 inches wide, the software will flat out refuse to do it.
It won't just squeeze it in.
No, it won't create a rung 10.5 just because you click there. It enforces the grid you established.
So you simply can't force it to violate its own structural rules.
Exactly. If you need space, you have to move things first. You have to use the scoot command, which we'll definitely get into later, to physically push the existing rungs apart and open up a mathematically valid slot for the new rung.
It really forces you to maintain drafting standards. Now, what about if the numbering style itself changes? This is a scenario they brought up that gave me anxiety just reading it. You do the whole project using standard numeric referencing, 1, 2, 3. You finish 50 pages. Then the project manager walks into your office and says, actually, the client standard requires an A prefix on all control lines, so it needs to be A1, A2, A3.
That as a total nightmare scenario in standard CAD.
Oh yeah, you'd be double-clicking text boxes for days.
You'd be manually editing thousands of text fields, and you'd definitely make a typo. But in electrical, it's a non-issue. You use the Revise Ladder tool. You just select the ladder, change the start index from 1 to A1, and hit OK.
And it just fixes it.
The software recalculates the entire stack instantly.
But wait, it's not just the line numbers floating on the left side that have to change, right? What about the components?
And this is the crucial part that really separates this from basic drafting. Any component attached to those lines almost always derives its name, its tag, directly from the line number.
Oh, so they are linked.
Exactly. So if you have a relay, and let's say relay 10 is sitting on line 10, when you use Revise Ladder and line 10 suddenly becomes line A10, the software can automatically rename the relay to relay A10.
That ripple effect is incredible. That saves hours and hours of reconciliation work.
And it ensures you don't have mismatched tags between your schematic and your bill of materials.
Now, before we completely move off ladders, there is a variation mentioned in the source that I think really confuses people who are mostly used to basic house wiring or simple electronics, and that's the three-phase variation.
Right, so everything we've discussed up to this point, the standard vertical ladder that is strictly for control circuits, the low voltage stuff, the brains of the operation.
Nervous system.
Right, but the heavy lifting, the actual high voltage power distribution to massive industrial motors, that is almost always three-phase power. And traditionally, three-phase buses are drawn horizontally, not vertically.
So we take the concept of the ladder and literally tip it on its side.
Essentially, yes. The main bus rails run horizontally across the top of the page, or sometimes the bottom, and the rungs are vertical slices connecting down to the motors. You can change this orientation very easily in the initial ladder setup settings.
However, SunTech highlights a trap here. A big one regarding page limits.
The dreaded paper size trap.
Let's walk through it.
So imagine you are working on a standard 11 by 17 sheet of digital paper. It's 17 inches wide, but it's only 11 inches tall.
Makes sense.
If you take a vertical ladder that you designed to be 15 inches tall, which fits perfectly on a portrait page, and you suddenly tell the software to rotate it 90 degrees to make a horizontal bus,
It's going to run right off the bottom of the page.
you are drawing right off the edge of the world into the void.
The software won't stop you.
It will try to do what you told it to do. So whenever you switch orientation from vertical to horizontal, you absolutely have to check your drawing properties limits to ensure the bus actually fits within the physical borders of your title block.
Just a little detail that will ruin your printouts if you forget it. Okay, so that thoroughly covers the ladder. That is the standard, classic North American way to map the nervous system. But Section 3 of our outline introduces a completely different paradigm, the XY grid system.
This is a major shift in how you think about the schematic. The ladder is inherently sequential, line 1, line 2, line 3, that flows linearly down the page. The XY grid system is coordinate-based. It treats the drawing sheet exactly like a map.
You know, the analogy that immediately came to mind when I was reading this section was the board game Battleship.
That is actually the perfect analogy. It works exactly like Battleship. You define zones on the paper. You might have numbers 1 through 9 running horizontally across the top of the page. That's your x-axis.
Right.
And then you have letters A through F running vertically down the side. That's your y-axis.
So under this system, the component isn't located on line 10. It doesn't care about rungs. It's located in zone B4.
Correct. And this system is incredibly common in European standards, the IEC standards, or in specific industries like automotive manufacturing.
Why do they prefer it over ladders?
Because their drawings tend to be extremely dense. They have massive, complex components that simply don't conform to a clean rail and run visual style. The grid allows for a much more flexible, almost free-form placement of components because you aren't tied to a specific run spacing. You just put it where it fits best on the grid.
But there is a huge caveat mentioned in the source regarding grids. They call it the silent failure. And it sounds incredibly frustrating for a new user trying to figure this out.
Oh, this is a classic gotcha. I've seen seasoned engineers pull their hair out over this.
Walk us through it.
Okay, so you decide you want to use a grid. You go into the drawing properties dialog, you switch the format referencing from reference numbers to XY grid, you set up your zones, maybe 9 by 6, and you hit OK.
Everything seems fine. The software updates its internal math. It knows the grid is there.
It absolutely knows the database is updated. But then you look at the screen.
And the screen looks completely blank.
The screen is entirely blank. The borders of your page are empty. The grid exists mathematically in the background, but visually, there is absolutely nothing there to guide you.
That is wild. Why wouldn't it show it?
Because you have to explicitly check a tiny separate box in a different menu that says Insert XY Grid Labels.
So if you don't check that specific box, you are flying completely blind.
You are. You start placing components, and the software is automatically naming them based on a grid that you literally cannot see.
You drop a relay somewhere in the middle of the page, and it automatically names itself CRB4. And you're sitting there thinking, where on earth did B4 come from?
Exactly. It came from the invisible grid that you forgot to label. So the pro tip here is always turn on the labels first.
And that naming convention, the CRB4, that is the smart connection between the grid and the component, right?
Yes. In AutoCAD Electrical, a component's name, its tag, is essentially its physical address. In a ladder system, the address is the line number. But in a grid system, the address is the zone coordinate.
And this all goes back to helping the maintenance technician.
Exactly. When the tech sees CRB4 on an error readout, that tag tells them exactly where to look on the giant physical schematic printout. Go to column 4, go down to row B, There it is.
This leads perfectly into a nightmare scenario mentioned in the text, retagging. They call it the midstream switch.
This happens way more often than you'd think. It's usually when a project starts with one engineering standard and then suddenly switches to another halfway through.
Because the client changed their mind.
Always. So imagine you start the project in standard ladder mode. You've drawn 10 pages, you've placed 50 relays. The software automatically named them CR1, CR2, CR3 based on the ladder lines. Perfect.
Yeah.
Then the client calls and says, actually, our corporate standard requires XY grids for all schematics.
So you go into properties, you change the settings to grid, you turn on the labels, but the component names don't change automatically, do they?
No, because the components are fundamentally dumb in that exact moment. They are stubbornly holding on to their old hard-coded addresses. CR1 is still named CR1, even though line 1 conceptually doesn't exist anymore on that page.
So the drawing is a grid, but the labels are still acting like a ladder.
Exactly. You have to manually run the revise ladder, or the renumber command for the entire project. This forces the software to look at the new grid layout, calculate the new XY coordinates for every single device, and update every single tag to match the new logic.
So CR1 suddenly updates to become CRA1.
Right. If you forget to run that update command, you end up with a drawing that is mathematically a grid, but visually filled with components named after a ladder. It's wildly confusing and looks incredibly unprofessional.
The major lesson there seems to be, pick your system ladder or grid before you draw the very first line.
Plan the work, then work the plan. Don't change midstream if you can help it.
It brings me to a final, slightly provocative thought to end on. We have spent this whole time talking about how smart the software is.
Or smart.
It auto-increments 50 pages of numbers to save us time. It magically flips wires around corners so they don't cross. It warns us about adding rungs where they physically don't fit. But the source material also highlighted how incredibly easy it is to accidentally dead short an entire factory floor just by lazily clicking the bottom wire instead of the top wire.
Yes, that is the paradox of the tool.
It makes you realize that the software handles the heavy lifting. It handles the tedious repetition, but the actual logic, the crucial engineering decision of exactly where the power flows and what it does, that relies entirely on the human operator's understanding of the system.
The software has incredibly strict rules, but it has absolutely no wisdom.
Which makes me wonder, we spend so much time learning to think in grids and ladders simply because that is how the software demands we organize the data. Are we actually designing the best possible circuits, or is the software's design forcing us to organize our human thoughts to perfectly fit its database structure?
That is the eternal question of automation, isn't it? We shape the tool to help us, and then inevitably the tool shapes how we think. The whole XY grid system is a perfect example of that. We are literally adapting our engineering language to make it easier for a database to index our work.
We are organizing our own minds to fit into the zone.
We really are. We become part of the machine.
Well, while you, the listener, wrestle with that philosophical nugget, and before you fire up the software to start your next massive ladder logic project, please, I beg you, check your templates first.
Metric or imperial. Pick one and stick to it.
That is the absolute golden rule. Thanks for diving deep with us into the mechanics of AutoCAD Electrical. Go out there and draw some intelligent nervous systems.
Happy engineering, everyone.
See you on the next deep dive.
Thank you for watching the full video. Don't forget to subscribe to the channel and ask your queries in the comments below.